Let's look at an example where we have to find the empirical formula of a substance, and we are given the percentages by mass. So really in this problem statement, it should say somewhere that the percentage composition by mass is 70% manganese and 30% oxygen. So when we're doing this, we're used to converting grams into moles by using the molar mass. So if we're given percentages, what's nice to do is to assume that you have 100 grams. So that way you can change percents directly into grams. So by assuming I have 100 grams of the entire substance, I can say, all right, I have 70 grams of Mn, and I have 30 grams of O. Now, what's important to note is that this is not O2. When oxygen is by itself, it's diatomic, because in nature it's found as O2. If it's in a compound, it might have any subscript. I don't know what the subscript is because I don't know the formula. So I'm just treating this as oxygen right now, not diatomic oxygen, just oxygen. Okay, and because just think of, like, you can have carbon monoxide, CO, you can have carbon dioxide, CO2, you can have sulfur trioxide, SO3, so there's a bunch of different subscripts that are possible for oxygen in a compound. Okay, so now I'm in grams, and what do we say? When in doubt, what do? We mole it out. So basically, when we're dealing with formulas are always on either an atom ratio on a very small scale, like for carbon monoxide, there's 1 C for every 1 O atom, or on a larger scale, they're mole ratios, 1 mole of C for 1 mole of O. But they're never on a mass ratio when we're looking at the actual subscripts. The subscripts represent mole ratios, so that's why we have to mole it out. So to mole it out, we're going to use the molar mass. So we've got to look up the molar mass of manganese, and be careful, that's Mn, not Mg, and oxygen. So for manganese, okay, I want grams on the bottom, I want moles on top, I want grams on the bottom so that it cancels out with the other grams, and I can look up on my periodic table, and there's about 54.9 grams in every 1 mole of manganese. And if I divide this out in my calculator, I get that there should be about 1.275, let's say, moles of Mn. When you're doing this, it's really useful to keep a lot of significant figures until the very end. Because if you don't keep enough significant figures, you don't keep enough digits, then you're not going to end up working into nice whole number ratios. So don't worry about sig figs right now. Keep as many digits as possible for right now. Okay, and I'm going to do the same thing with oxygen. I want grams of oxygen on the bottom. I want moles on top so that I cancel out grams and I'm in moles, and I look it up, and there are 16 grams in every 1 mole of oxygen. Again, I'm just dealing with this as a single oxygen atom right now because I don't know what the subscript is. It's only diatomic if it's an element, and this is not an element, it is a compound. So I do 30, and I divide it by 16, and I get 1.875 moles of oxygen. Now, technically, this is the formula right here. Mn would have a subscript of 1.275, O would have a subscript of 1.875, but we're not used to seeing formulas like that. What do? We use whole numbers. So what I'm going to do is I'm going to divide by the smallest mole, so that I can try to work these into whole numbers. So out of 1.275 and 1.875, 1.275 is the smaller number. So let's divide and see what we end up getting. 1.275 divided by itself is 1, and 1.875 divided by 1.275, it comes out to be about 1.5. So if I ever get something that has a 0.5, what I can do is I could just multiply the whole thing by 2, and I get 1 times 2 is 2, so I get Mn subscript of 2, and 1.5 times 2 is a 3, I get Mn2O3. That is my formula. And that makes sense. Manganese can have a 3+ charge, and oxygen has a 2- charge, and then it would make this formula. This would be manganese 3 oxide. So when you get to the end of your problem, it might require a little extra manipulation. But again, the steps are the same. If you have percents, assume you have 100 grams and turn the percents directly into grams. The problem might give you grams to start with, and then you omit that step. You always mole it out. Then you can divide by the smallest mole amount. That should bring you closer to whole numbers, and if you don't get exactly whole numbers, you might have a little bit more manipulation to do. A lot of times you'll end up with something 0.5, and you multiply it all through by 2. Whatever you do to one, you got to do to the other, just like in math. What you do to one side, you do to the other, so that overall you're making the same changes. You're not changing the equality.